Today, we're jumping into something really fascinating and honestly pretty futuristic. Embodied AI. Think smart robots in our homes, sophisticated AI helping us out, even the kind of immersive stuff we see in AR and VR. This isn't just science fiction anymore, it's happening now. But there's this surprisingly tricky challenge right at the core of it all. It's about creating the worlds these AIs learn in. Really realistic, diverse 3D virtual environments. Because that's the main hurdle. The bottleneck holding back truly general purpose embodied AI. It's just incredibly hard to build these complex 3D worlds, especially at the scale needed. Let me paint a picture. Imagine you have a new helper robot. Simple task. Get the blue mug from the kitchen. Okay, so in its training world, maybe the kitchen is super simple, like really basic. It tries, it fails, keeps bumping into the fridge, maybe gets stuck on a chair. And it's not that the robot itself is dumb, not at all. The problem is the training space was just too neat. Too predictable. It didn't see the messiness of a real kitchen, right? Where the mug might be behind some mail or on a different shelf or half hidden. It just couldn't generalize from that clean digital space to, well, real life. And that really shows the limits of the old ways of training. We need much better virtual proving grounds. So what's the big idea, the innovation that's starting to break through this? Well, it involves using large language models, LLMs, to automatically generate these complex, realistic 3D places. And today's deep dive is all about a system called prompt-to-perception. It's basically showing how plain language, just words, can become the blueprint for building these virtual worlds for AI training. Pretty cool, right?
Absolutely. And that robot example, it perfectly highlights why the traditional methods just aren't cutting it anymore. For a long time, creating these environments was a huge pain point for AI development. You had manual modeling first, which is exactly what it sounds like. People, highly skilled artists, building everything piece by piece. It takes an incredible amount of time, just imagine. And it's definitely not scalable if you need, say, thousands of unique kitchens or offices.
Right, you need an army of artists.
Exactly. Then you've got procedural rules. These try to automate things a bit, generate layouts based on rules, but they're kind of rigid. They struggle with the subtleties. They can make a room, sure, but capturing the difference between like a cluttered artist studio and a minimalist office based on how things are arranged, that's tough for them.
They lack that semantic understanding.
Precisely. And the third main way was 3D scanning, capturing real-world places. That gives you amazing visual detail, high fidelity. But the downside is those scans are often static. They lack interactivity. You can't just easily move things around or change the layout for training variations.
Okay. So they look real,
Okay.
but the AI can't really interact with them in a meaningful way for learning complex tasks.
That's often the case, yeah. And these aren't small problems. These limitations really hold back training agents that can do zero-shot transfer. That's the goal, right?
Yeah.
An agent learns in one setting and can then apply that knowledge to a totally new, unseen situation without extra training for that specific situation. And these older methods just make getting there really, really hard and inefficient.
Okay, that perfectly tees up the need for something new. And this is where the aha moment comes in with LLMs. Because I think most of us, we still think of LLMs as these amazing chatbots, great for writing or summarizing. But what's really mind-blowing is there's so much more. They seem to have this huge amount of common sense knowledge baked in. They understand space, how objects relate to each other, what objects are, and how we use them. It's not just about predicting the next word. It's deeper. They can take a description, something quite detailed, like a sunroom with floor-to-ceiling windows and a potted fig tree in the corner, and actually understand the implied structure, the right kinds of objects, the layout. That semantic capability is the game changer. It lets them create virtual scenes that actually match how we understand the world. It's almost like they learned about the physical world just by reading everything on the internet.
Exactly right. And prompt perception harnesses that exact capability. Let's maybe walk through the steps, because it's fascinating how it goes from just text to a fully interactive 3D world. Okay, step one is super simple. Natural language input, you just type what you want, like a cluttered workshop with scattered tools, a workbench in the center, and shelves filled with electrical parts. Or something maybe more whimsical like, our researcher's cat-filled apartment with books overflowing from shelves.
I like that one. So you just describe it.
You just describe it. Then, step two, modular prompting. This is clever. Instead of giving the LLM that one big description and saying, go figure it out, they query it with specialized prompts for different parts of the job. So there's a floor plan module that figures out the room, shape, size, maybe wall and floor materials.
Okay, the basic box.
Right. Then a window door module. Displays openings, defines how spaces connect, where light comes from, topology, basically.
Makes sense.
Then the object selection module. This is where the LLM's knowledge shines. It picks appropriate 3D models from big libraries, like Objaverse is a popular one based on the prompt. So for the workshop, it finds tools, benches, shelves.
Using that semantic understanding we talked about.
Exactly. And finally, the layout module. This doesn't just place objects randomly, it suggests relationships, like tools near the workbench, or parts on the shelves, chair in front of the desk.
Wow, okay. That modular approach seems really smart, breaking it down.
Yeah.
So the LLM generates all these instructions, floor plan, objects, where they should go. What's next? How does it actually, build the thing?
Right. That leads to step 3, scene assembly. This is where it becomes a virtual reality. They use simulation engines. Common ones are AI2 Theagora or Habitat. The system pulls the 3D models chosen by the LLM from the repositories, and then it has to figure out the exact placement based on those relational constraints, like near or on. This uses constraint satisfaction algorithms. You might hear terms like DFS, which is depth first search, or milk mixed integer linear programming.
Okay, fancy terms for basically puzzle-solving algorithms.
That's a great way to put it. They make sure objects don't crash into each other, that they respect the physics and logic of the scene. So yeah, a chair doesn't end up halfway inside a table. And then there's some final cleanup, like mesh simplification to make it run fast, setting up colliders so objects interact properly, making it ready for physics.
So it's not just a picture, it's an interactive space.
Precisely. Which brings us to step 4, agent integration. The scene is built, it's ready. Now you drop your embodied AI agent into this virtual world, and you train it or you evaluate it on different tasks. Could be basic stuff like object nav, find the blue mug, or more complex things like semantic rearrangement, tidy up this workshop according to some rules. Or even following complex instructions. Go pick up the screwdriver from the workbench, put it in the toolbox, and then close the lid.
Okay, wow. That whole pipeline is quite something. So let's circle back. Why is this such a big deal for everyone listening and for AI research generally? I mean, it feels like more than just making things faster. It feels fundamental. First off, the scalability is just off the charts, right? Instead of spending weeks or months crafting one environment, you can generate potentially limitless variations just by writing different descriptions. Think about the sheer amount of training data that unlocks. It's staggering. It's like moving from hand-carved sculptures to 3D printing on demand, but for entire worlds. It's not just quantity, it's quality too, right? The realism and diversity. We're not just talking visual realism, but functional realism. You can generate kitchens, labs, factories, classrooms, gyms, you name it. And the objects inside make sense for that context. This is huge for preparing agents for the messiness and unpredictability of the real world and the payoff you mentioned earlier. The generalization. Agents trained in these richer, more varied LLM-generated worlds, they actually perform better when they encounter new situations they'd never seen before. That's how you get things like zero-shot navigation, navigating a brand new place successfully first try.
Exactly.
And it opens the door to broader task planning. These were massive roadblocks before. So yeah, it really does feel like a transformative shift from painstaking design to just talking the worlds into existence.
And we have ways to measure how well this actually works. The evaluations are pretty compelling. There are quantitative metrics like CLIP-based visual textual alignment scores. That's basically using another AI model, CLIP, to check how well the final 3D scene matches the original text prompt. A high score means it did a good job capturing the description visually.
So an AI checking another AI's work.
In a sense, yes, but then there are also human preference ratings. You ask actual people, does this look realistic? Is the layout functional? Does it make sense? Human validation is still critical.
Right. Does it feel right to a person?
Exactly. And maybe the most important evaluation is the zero-shot performance benchmarks. You train an agent in these LM-generated scenes, then you test it in completely new environments it's never encountered. And the results show these agents generalize much better, performing tasks successfully even in unfamiliar territory. That's the real proof in the pudding.
Okay, so summarizing the big strengths here. We've got scalability, obviously, creating tons of scenes quickly. We've got incredible semantic control. You fine-tune the world just by changing your words. It's like having a superpowered level editor you just talked to. Unmatched diversity, both in looks and function, which leads to broad cross-domain utility. Useful for training robots for homes, factories, hospitals, schools, pretty much anywhere. It really is that shift from static design to dynamic, language-driven creation. Now, it sounds amazing, but no system's perfect, right? Especially cutting-edge ones. What are the main limitations or pain points right now? Where does it still struggle?
That's a very important point. Transparency about limitations is crucial. One big one is asset dependency. The system can only build scenes using the 3D models available in its libraries. So, if you ask for a researcher's apartment filled with rare 18th century scientific instruments and 3 Persian cats, but the library only has basic furniture and maybe one generic cat model.
You're not going to get exactly what you asked for.
Exactly. The output quality and specificity are bound by the input assets. Another challenge is layout robustness. Those constraint solvers, the puzzle solvers, they're good, but sometimes they fail. You might get scenes where objects are overlapping weirdly, or the layout just doesn't quite work, requires fixing.
Okay, so occasional glitches in the matrix.
You could say that.
Yeah.
And then there are practical costs. Compute and API cost. Generating complex scenes, especially using the most powerful LLMs via APIs, requires significant computing power and can run up cloud bills. It's not free.
A real-world constraint.
Definitely. And finally, what I'd call a feedback loop deficiency. Right now, editing a scene after it's generated using language isn't super fluid. You can't easily just say, okay, now move that lamp 6 inches to the left. It's not quite a real-time conversational design process yet.
Got it. Those make sense as current hurdles. So looking forward, what are the next big steps? What are you most excited about seeing?
Oh, there's a lot of exciting potential. Building on that feedback loop issue, imagine LLM-guided scene repair. What if the agent itself, when it gets stuck, could suggest changes to the environment? Or even trigger regeneration, a self-improving world?
Whoa, that's meta.
Right. Then there's leveraging multimodal scene understanding. Using models like GPT-4V that can understand images and text, they could look at potential assets and make even Billy choices or understand context from reference images.
Bringing vision into the loop.
Exactly. And that feeds into the dream of a truly interactive design loop, real-time dialogue. You describe, the LLM generates, you refine with more words, it updates instantly, like having a conversation with your design tool.
That would be incredible.
And ultimately, it's about advanced robotics integration, training agents for much more complex real-world tasks, using tools precisely, assembling objects, maybe even collaborating with other robots or humans in these generated spaces. Which, of course, also means we need bigger, better asset libraries and the ability to simulate ever more complex task physics and interactions, pushing closer and closer to reality.
It really feels like we're just scratching the surface here. So to wrap things up, this LLM-based approach, prompt to perception, and similar ideas, it really is a paradigm shift, isn't it?
I truly believe so. It fundamentally changes how we create these crucial training environments. We're moving away from needing deep coding or 3D art skills for every single environment towards using our natural language. And what's profound is that the LLMs aren't just following instructions. They're using their world knowledge to act as architects. They're building these intelligence-rich environments, the sandboxes where AI learns to be intelligent.
Architects of intelligence-rich environments. I like that. And that leads to the final thought for you, our listeners. Language is now a tool not just for talking about the world, but for actually building virtual worlds. Think about that. If we can generate complex, realistic simulations just with words, what does that really mean for the future? How will we interact with AI? How will we train it? How might we even define intelligence itself when we can speak its learning environments into existence? What new realities, virtual or otherwise, does this unlock? Definitely something to ponder. Join us next time for another deep dive.